So here we are at the last video for this particular CCNA EIGRP lab, where we're going to do some path manipulation. So at present, when router 1 is pinging the loopback of router 4, I can expect that it's going to take this fast Ethernet link. How would I actually prove that? Well, here's what we're going to do. Let's go ahead and start the routers up. And let's go into router 1, and what we're going to do is we're going to look in his routing table. And we're going to see, according to his routing table, if he was going to route packets to the 444444 network, what would his egress interface be? Where would he send those packets? Show IP route. And we can see he's learned of that network, and he would route them out the fast Ethernet link, just like we thought. Okay, now we also saw previously, if we did show IP EIGRP topology all-links, we did see that he had learned about that route via the slow speed serial. So what we need to do is we need to ultimately make EIGRP follow the top link. We have to trick it or fool it into thinking that the top link is actually the better path. Well, let me ask you a question. By default, when EIGRP is coming up with its metric, that big long number that we call distance, what are the variables that it plugs into the formula to come up with its distance value? What are the default variables, otherwise known as vector metrics? Well, hopefully you quickly answered bandwidth and delay. Bandwidth and delay are part of that formula, the default formula. Now, it's recommended that you do not touch the bandwidth on an interface because bandwidth is used by other things as well. So ideally, if you want to manipulate EIGRP, you're going to manipulate the delay variable. So let's go ahead and start by doing this. Let's go ahead and in here, let's try to take this interface right here, serial 2/0, and let's lower the delay. Actually, let's lower it to the minimum value and see if that works to get our desired result. All right, so let's go into router 1. Actually, I'm not sure if when I took my last snapshot I had the routers turned off or not. So I'm going to go ahead and retake that snapshot because I suspect I did not. Okay, so now let's turn them all back on. And let's go into router 1 and go onto a serial 2/0 and reduce the delay to the minimum possible value to make it look like there's hardly any delay on that interface at all. Interface serial 2/0, and we'll say delay, and the lowest number I can select is 1, which actually, because it's tens of microseconds, means I'm telling him the delay on that interface is 10 microseconds. Save my config. Show IP EIGRP topology. And remember, the way this works is that after your prefix or your network, what you'll see first in this output is the successor, or if you have more than one successor, the successors, followed by the feasible successors. Okay, so in this particular case, it's still using fast Ethernet 00. Nothing has changed. Okay, that being the case, let's go back to our topology now and try lowering the delay on this upstream interface and see if that will also work. So that is, well, what is that? That is serial 2/1 on router 2. We'll minimize this. Actually, we'll maximize it, and let's go back to router 2. Interface serial 2/1, delay of 1. Save that. We're not going to need router 2 anymore. Close him down. All right, did that make router 1 switch over? Nope, still using the fast Ethernet. Okay, now before we resort to modifying bandwidth values, is there anything else we can do with delay? Well, in our topology here, we lowered the delay of these as far as we can possibly go. Why don't we take the reverse approach now? And why don't we go to router 1's upstream interface and increase the delay to some really horrible number. So he thinks that anything going out that interface will experience a lot of delay. So let's go back to router 1. We're still there. Interface fast Ethernet 0/0, delay, and let's give him some delay of like 55,555. So 55, that's tens of microseconds, so that'll actually be 555,550. Okay, did that make him change? Nope, still using that fast Ethernet. He hasn't switched over yet. Oh, there we go. It did work. Look at that. Now the 44 network, the next line, which is the successor, is showing as serial 2/0. And if we do show IP route, we can now see that the 44 network is indeed going across the top path, the serial link. And I can verify that by doing trace 44.44.44.4. And we can see the first hop was 1.2.1.2, which was right here, router 2. And then the next hop was 2.4.2.4, which was this address right here. Now, as of this point, I'm going to go ahead and stop the video at this point. We're not entirely done, so if you're doing this on your own, you're almost there. We've got packets from router 1 going to router 4, taking the top link. But that's not going to affect the return traffic. Router 4 is still going to believe that to get back to router 1, he should go across this bottom path. So right now what we have is what's called asymmetric routing, where packets going in one direction take one path and the reply packets take another. How can we verify that? Well, let's go to router 4. And let's see if he was to ping back to the 11 network, what path would he take? And we can see that right now he's still taking the lower link. So in order to complete this lab, you're going to have to continue manipulating metrics until router 4 also believes that he should take the upstream serial link. And just in case you get stuck with that, what you're going to do is sort of the reverse of what we just did. So you're going to, on router 4, minimize the delay on this interface down to 1, minimize the delay on this interface down to 1, and then you're going to want to maximize or really increase the delay on the fast Ethernet interface to make it look like it's just horrible and you don't want to go that direction. And that will allow router 4 to take the top link. And that concludes this video series on our CCNA EIGRP lab using GNS3.